The topic of this video is autocorrelation. But before diving into that, let's just think about simple correlation. And I want to go over this in what might be a slightly different way than what you've seen before, in that I'm going to focus on, in defining the concept of correlation, this idea of expected value. So here we have height and weight. You can see they're correlated. We have here the average height. We can think of as the expected value of height. And here the average weight we can think of as the expected value of weight. And let's take someone that's in this particular height class. So individuals in this particular height class, there they are. And if you look at the average weight of those folks, the average height of these individuals was greater than the expected value of height. The average weight of those individuals is greater than the expected value of weight, because these data are correlated. And here we have some uncorrelated data. So again, we'll take, here we're looking at age versus height. And presumably for people that are reasonably old. And what we discover is if we take this particular age class, and there are all the folks in that age class, if you think about their average height, then the average height of those individuals is going to be equal to the expected value of height, even though those individuals are in an age class that is greater than the expected value of age. So in the case of uncorrelated data, the effect of age has no effect on height. So obviously we're dealing with adults, or it doesn't, in a population that doesn't include children. Okay, so with that introduction, what I want to do is I want to simulate some data to get a better handle on this idea of autocorrelation. And I want to begin with some uncorrelated data. I'm going to simulate some uncorrelated data. And I'm going to start off by, first value is going to be y1, and that's going to be equal to starting off with an expected value of 5 and adding to it a little residual taken from a normal distribution with mean 0 and standard deviation 0.2. And then y2 is also going to start off with the expected value and add a similar residual, and y3 is going to be exactly the same. So these are uncorrelated. And the concept of uncorrelated is if this value here of y1 happens just by chance to be greater than the expected value of the random variable y, that has no influence whatsoever on whether or not y2 is going to be greater or lesser than the expected value of the random variable y. So now I want to think about autocorrelated data. I'm going to simulate some of those, and I'm going to start off with y1 just as before. Start off with the expected value of 5 and add to it residual, and I'm going to say is normally distributed with mean 0 and standard deviation 0.2. And I can identify this thing as, I'm going to call this residual 1. Now what's going to happen, however, when I make y2, I'm going to start off with the expected value of 5. Going to add a little bit from a normal distribution, mean 0, standard deviation 0.2, and then I'm going to add another component that consists of 0.7 times this residual 1. And then I'm going to make y3. I start off with the expected value of 5, add to it a random bit from a population that's normally distributed mean 0, standard deviation 0.2, and then I'm going to add to it, and I'm going to consider this whole thing here to be residual 2, add to it 0.7 times residual 2, and then y4, the same thing, 5 plus n 0 0.2. This is residual 3 plus 0.7 times residual 3. And you can see what's happened is that these values are no longer independent. That the value of y4 is going to inherit some of the residual, some of the error variation from y3. So you're not going to have independent values anymore. They're going to be correlated. And so let's say we did a whole series of values that were either obtained through this process or through this process. And here we see some autocorrelated data. And here we see some uncorrelated data. And you can see in the case of the uncorrelated data generated by that process that you really get scattered up, down, up, down, up, down, up, down like that. In contrast, if you've got data that are generated through a process of autocorrelation, each one of these values inherits some of the residual from the previous value. So if this guy was above average, well, then the next guy is likely to be above average too, and above average, and above average, and above average, and above average. And here we got a bunch that were below average, but then all of a sudden, it got about 4 in a row where the little bit that was added was above, and then it got above average, and then it stayed up here for a while. So with autocorrelated data, what you see is a pattern. You can see it, think about it in a couple ways. You kind of got clusters, like there's a cluster above, and a cluster below, and a cluster above, and a cluster below, a little cluster below, or you can think of it as kind of generating an overall wave pattern that's not going to be present in the case when you've got uncorrelated data. So in this figure, what I want to do is talk about the concept of lag, which is very important when you're dealing with autocorrelation. So in A, we're having autocorrelation with a lag of 1. So what does that mean? What it means is we've got a whole series of numbers that are shown here. And I'm going to take the first number, 5.07, I'm going to put that on the x-axis, and I'm going to jump 1. I'm going to have a lag of 1 and put 5.13 on the y-axis. So it's going to be probably something like about there or so. And I'm going to move over 1. I'm going to put 5.13 on the x-axis, jump 1, and put 5.08 on the y-axis. And again, maybe a point right there. And I continue on. So when I get out here, I put 4.75 on the x-axis, jump 1, lag of 1, 4.83 on the y-axis, probably someplace like that. And I continue on and on. So that is a lag of 1. So what we have on the x-axis, on the horizontal axis, is the nth value. The nth value in this sequence of numbers. And what we have on the y-axis is the n plus 1th value. So you see a correspondence between the first and the second and the third. Looks like about the 1, 2, 3, 4, 5th and 6th, something like that. Now, in C, what we've got is a lag of 7. So we put 5.07 on the x-axis, and we go over 1, 2, 3, 4, 5, 6, 7, 8. We add 7 to it, get 4.78. That goes on the y-axis, so something that looks like about there, I would guess. And then we move over 1. We get 5.13 on the x-axis. 1, 2, 3, 4, 5, 6, 7, 7. And we get 4.98 on the y-axis, so 5.13, 4.18, something like that. And we continue on with that process. So that's a lag of 7. So it means on the x-axis, we've got the nth observation, and on the y-axis, we've got the n plus 7th observation. Now, the pattern here is really quite important, because what you see is that with autocorrelated data generated by the kind of process that I described up here, what happens is when you do just a lag of 1, then you see that the data are in fact quite strongly correlated. On the other hand, if we make this big lag of 7, then the correlation is lost. And that's really, I shouldn't draw a line like that because there is no pattern. Essentially, it's a flat line. And that's what typically we see with autocorrelation. As the lag increases, the autocorrelation goes down. Interesting thing to note is, why do we call this autocorrelation? We think of typical correlation, height, weight. You've got two variables, height and weight. Here we don't have two variables. We've only got a single variable. We've got a sequence of values in a single variable. So what you really got is a bunch of numbers that are essentially, since we've only got one variable, correlated with themselves. Internally, so we think of that as autocorrelation. Why do we worry about autocorrelation? So let's say we've got a field and we're thinking about taking some soil samples, and there's a gradient of fertility so that the dark here is highly fertile and the light is not so fertile, and here we have random sampling. In contrast, in panel B, we've got the same field, but now we're going to go on a random walk. And as a consequence of going on the random walk, the value that you get right here is partly dependent on what you saw here, and the value you get here is partly dependent on this value, which in turn is partly less. So you can see that with a random walk, the values are going to tend to be, the samples are going to tend to be autocorrelated. And you can see why this would be a problem, because right here, you're sampling pretty much throughout the entire field. Whereas in this case, just because of chance, because you have this autocorrelation, it started off in this dark side and it lingered in this dark side. So you're not going to have a very efficient sampling method. And so we can think about this idea of effective sample size. So that the effective sample size, when you've got a random walk with autocorrelation, is going to be less, even though there's 8 observations. The expected sample size, and I'm just making a number up, might be, the amount of information might only be equivalent to 6 samples had they been taken randomly. And so why this can be a problem, another reason why this can be a problem, is that if we think about taking a running average of values, and here we have an autocorrelated sequence of data, so we're taking a running average, and it takes a large number of iterations before we finally settle down on the true average value. Whereas with uncorrelated data, with truly random sampling, we very quickly, if we think about taking a running average, we very quickly center down to the true average. So, bottom line, autocorrelation is a feature of random walks, sort of thing that we're going to see in MC sampling, Markov chain Monte Carlo sampling, and it's going to tend to reduce the efficiency. And we also saw that lag size is important and that autocorrelation tended to decrease with increasing lag size.